Guys, so today we are going to be looking at predicting the products of a chemical reaction. Most of this stuff is going to be review from stuff we did before the break, but I think there was a little bit of confusion then, and it's been multiple weeks since we've done this, so I think this review will hopefully be pretty helpful. So let's just jump right into it. Our goals for today: first, we're going to review the 5 major types of reactions. Then we want to practice identifying the type of reaction based solely on its reactants. And then we are going to look at actually predicting the products of a chemical reaction based on those reactants as well. Starting off with reviewing the 5 major types of reactions. Hopefully you guys all remember this, but the 5 major types of chemical reactions are synthesis/combination, decomposition, single replacement, double replacement, and combustion. And if you're following along right now with the chemical types reaction reference sheet, I'm not 100% sure exactly what it's called. It'll be posted up in the classroom. These will all be spelled out for you as well. So first, let's look at synthesis and combination. Synthesis and combination reactions occur when 2 or more reactants combine to form a single product. The general formula for these combination reactions is A plus B goes to AB. A and B can be single elements, or they can be small covalent compounds as well. Usually, for the sake of our class, they're going to be single element combining to form a product. A lot of times you'll see this with like potential ions, so sodium plus chlorine goes to sodium chloride, stuff like that. A common example, the one given here, is the formation of magnesium oxide from magnesium metal and, of course, oxygen when exposed to enough heat. Decomposition. Decomposition reactions occur when a single reactant breaks down or decomposes to form multiple products. So generally speaking, what you're going to see, it gives you the general formula there, which is AB goes to A plus B. Generally, if you see a single reactant that's just a big thing, it's going to be a decomposition reaction because it's not adding anything else to it. It has to be breaking down. And the common example of a decomposition reaction is the breakdown of hydrogen peroxide, or as we saw in class, a very poor demo of elephant toothpaste. Single replacement. Single replacement reactions occur when a single element replaces a part of a compound. The general formula for a single replacement reaction is A plus BC goes to AB plus C. And we're going to talk a lot more about single replacement reactions in the next lesson, actually. We'll be looking at the activity series of metals. But a common example of a single replacement reaction is the dissolving of solid aluminum in aqueous copper chloride, and that is the lab we did just before we left. We put the aluminum foil into that blue solution. You had a sort of like rust type looking thing, which was actually just solid copper forming. Well, the aluminum dissolved into the solution, turning it into a more murky silverish white color. But that reaction is Al plus CuCl2 goes to Cu plus AlCl2. Double replacement. Double replacement reactions occur when 2 ionic compounds swap their cations. So really, they just swap everything, but it's easier to think about it as switching the positive on one with the positive on the other, or the negative on one with the negative on the other. Either way, you're going to end up with the same general formula, which is A positive, B negative, plus C positive, D negative, goes to C positive, B negative, and A positive, D negative. Just remember with those, the charges don't actually need to be written in the formulas themselves. Those are just the ions that are formed if those compounds are separated. Generally speaking, if you recall, when they're aqueous, dissolved in solution, they're going to be dissociated, so they're going to be existing as ions separate from each other anyway. Do make sure that your charges are balanced when you're balancing these chemical reactions. You can't have, for instance, MgCl. You have to have MgCl2 because Mg needs needs to get rid of 2 valence electrons, and chlorine can only take 1. So you need 2 chlorines to bond to that magnesium. And you'll need to use periodic tables to double check those, but for right now, all the reactions we're going to be dealing with are already balanced for you, so you don't have to worry about that. A common example of a double replacement reaction is the formation of lead iodide, which is a yellow solid, from lead nitrate, which is a clear liquid, and potassium iodide, which is also a clear liquid. And lastly, we've got combustion. Combustion reactions occur when an element or compound, usually a hydrocarbon, react with oxygen, often producing energy in the form of heat or light. So most commonly we think of combustion as fire, and the most common version of combustion is in fact a hydrocarbon, which is any compound made of carbon, hydrogen, or sometimes oxygen as well. So things like sugars, wood, obviously, things like that. They're all going to be combustion reactions when exposed to heat and pure oxygen, O2. The general formula for a combustion reaction is CH with the X's and the Y's. Those subscripts are just to denote that you can't have just CH reacting with oxygen. It's usually going to be like CH4 or C3H8, or there's a bunch of different combinations, but C something, H something plus O2 goes to CO2 plus H2O. Your products from a combustion reaction with a hydrocarbon are always going to be just CO2 and H2O. Sometimes if we're using something else, like for instance, technically burning magnesium is a combustion reaction, so that would have a slightly different product. But we're mostly going to be looking at these ones, these hydrocarbon reactions, so your products are always going to be carbon dioxide and water. A common example of a combustion reaction is one that we use all the time in the lab, burning of methane, which is coming out of those hoses from the gas mains, gas lines, whatever they are. So CH4 methane plus 2O2, which is oxygen, goes to CO2 and H2O. So next we're going to look at identifying the type of reaction based on its reactants. In general, you can identify a reaction based solely on its reactants. This isn't always true. There are going to be some times where something might look like a single replacement, but it's actually a synthesis reaction, or might look like a synthesis reaction, but actually be single replacement. Those are usually the two that are the easiest to get mixed up. Decomposition is really easy to identify. Double replacement is usually pretty easy to identify, but not always. And then sometimes combustion, things like MgO, again, can get a little bit confusing and can actually fit multiple groups. All of the reactions that I'm going to be giving you on any assignments and on any tests, if we end up having tests while we're doing this online stuff, we probably won't for this unit, to be honest. But if you ever get tests on these things, they're going to be pretty definitively in one group, so hopefully it won't be too bad. And you will have that reference sheet that has all the different reactions, which you should probably get out, because next we're going to be looking at doing some practice. So for each of these, I'm going to give you guys some time to pause the video, take a minute to actually go through and try each of these on your own, identify the different types of reaction. I'll give you a hint. In this one, there is exactly one of each type. I made it easy for you, probably too easy. And then once I've given you some time to do that, we'll go over it together. All right, so hopefully with this first one, we were able to determine we've got a single element here with this potassium, and then we've got a compound of sodium fluoride here. So hopefully we were able to figure out that this is going to be a single replacement reaction. And you'll actually find out in the next lesson that this would actually not end up having a reaction occur at all, but we're not going to get into that right now. That is something for next time. This one, we've got a hydrocarbon right here. We've got oxygen right there, so we know that this is going to be combustion. All right. This one, we only have one reactant, Al2O3, so we know that that aluminum oxide is going to be decomposing, so this is a decomposition reaction. Ooh, handwriting just got a lot worse. Sorry about that, guys. I'm practicing with this new pen, so don't give me too much trouble for it. This next one, we've got a single element. We've got a single element in the form of a gas. It is diatomic, but there's only one element there. It's not really a compound, or at least not of multiple elements, so we know that this is probably going to be a synthesis reaction. And in fact, it is the synthesis of methane, also known as a combination reaction. And then this last one, I mean, you could do process of elimination here, but you see that we've got HCl, the hydrogen has the plus charge, chlorine has the minus charge in this case. We have CaCO3, so calcium is going to have a 2+ charge, carbonate is going to have the 2- charge. Since these are two ionic compounds, we know that we're going to be having a double replacement reaction going on here. So this is double replacement. I probably didn't need to write out, but I'm also going to start doing this shorthand, RXN. If I do RXN, that just means reaction. And it's because I don't want to write it out, because clearly I can't write with this pen. But anyway, moving on. Last thing we want to be able to do is predict the products of a chemical reaction based on its reactants. Now, we're going to have an entire another video where I go over some more examples of this later, but we're going to go ahead and work on it here as well. In order to predict the products of a chemical reaction, you first need to identify the reaction type. It will always help you to actually identify that reaction type right off the bat. And once you've done that, you'll be able to use the chart that you have, the chemical reaction types reference sheet. That'll tell you what your products should look like. We'll go through these, but individually, synthesis combination reaction, all you have to do is add the reactants together to form a stable product. So if you end up needing to have like two things in the product or whatever, like I said, for the most part, or at least for a while, I'm only going to give you guys balanced chemical reactions to begin with. So hopefully with synthesis reactions, all you're going to have to do is put them together and make sure you have the right number of both. Decomposition reactions, you break the reactant compound down into its most stable pieces. In this case, this can get a little bit confusing with some of the more complicated ones, but even with hydrogen peroxide, that H2O2 that we've looked at, that'll break down to form H2O and oxygen gas, diatomic oxygen, O2. And that is not as simple as breaking down into hydrogen gas and oxygen gas. That would be a lot easier than water and oxygen. So that's something that's going to come with just practice. But I'll try to give you equations that are fairly easy for now that will break down into elemental parts for the most part. Single replacement, we're just going to be replacing the correct part of the compound with your single element. The next lecture will also talk about when we don't have a reaction occurring at all with single replacement reactions, and that has to do with the reactivity series, which is what the next lesson is all about. So don't worry about that too much right now. All the ones that I'm going to give you for at least the time being are going to react, so you don't have to worry about that. And in that case, all you do is make sure you know whether or not the atom that you're adding into the compound is positive or negative when it forms an ion, and make sure you take out the one that has the same charge. Double reaction, really the easiest way to do it is just switch the metals from each ionic compound. Remember that ionic compounds are always going to have a metal and a nonmetal. Sometimes that nonmetal is going to look like something like CO3 or NO3 or carbonates, nitrates, phosphates, chlorates, etc. There's a bunch of them. So it's easiest to just switch the metals. And then lastly, for a combustion reaction, your products are always going to be some amount of CO2 and H2O. I'm only going to give you hydrocarbon-based combustion problems, so you won't have to worry about anything else. So we're going to do a little bit of practice on this one as well. There's going to be an entire practice worksheet, but I'm going to work through these ones in this video. I'll go ahead and give you a chance to pause so you can work on them on your own if you would like. All right, so for this first problem, we've got 3 hafnium plus 2 dinitrogens, probably a gas. In this case, we have 2 single elements forming together, so we know that this is going to be a synthesis reaction. And synthesis reactions, all we have to do is add ours together. We've got hafnium, there are 3 of them. Nitrogen, there are 4. So HF3N4. This one down here, we've got a single element here, and we've got a compound here, H2SO4. So we know that this is going to be single replacement, single rep. This magnesium has a 2+ charge. We know that in this case, the hydrogen is going to have a positive charge. So it's going to replace the hydrogen. And what we're going to end up with is H2 plus MgSO4. Next one down, we've got lead nitrate plus 2 sodium iodide. This one, we've got an ionic compound here. Lead is the metal. We've got an ionic compound here. Sodium is the metal. In this case, we know that if we have 2 ionic compounds, it's going to be double replacement. Double rep. And all we're going to be doing is switching these two. So you'll get, well, what you'd actually get if you did this is you flip these 2 NAs over here, you'd have Na2NO3 2, but we're just going to write that as 2NaNO3. Apologize if it's still hard to read. And then over here, we're going to have lead iodide, so PbI2. All right, and then for this last one, we've only got a single reactant. I actually talked about this in the lead up to this. That was kind of my bad. But because we only have a single element as our reactant, or single compound, sorry, we know that this is going to be a decomposition reaction. It has nothing else to add to it. It has nothing else to react with. Decomposition. I am struggling right now. And this one is actually going to go to H2O plus 2O2. There's not a 2 there. That should just be plus O2. And it's 2H2O. There we go. That's what I was looking for. So 2H2O plus O2. That way we have 4 hydrogens, 4 oxygens on both sides. So that is it for this video. Take a look at those practice problems. I'm going to go ahead and put out a video walking through a couple of them. I may or may not put the answers up to all of them. Depends on how grading and stuff is going to go and whether or not we're going to have a test for this one. But that is it for today. I will talk to you guys later.